rotation. So you always write the I alpha without the center. It's not rotating about the center. Why is it not rotating about the center? Because we have this acceleration. Well, this acceleration says we're not rotating about the center. Because the center is accelerating.
So you don't have to do the n squared, the parallel axis theorem or anything?
What you're going to end up with when you plug this in is m and then r squared alpha, so that it acts like the parallel axis theorem.
Oh. Okay.
That sort of makes sense.
I don't know, I guess when I was doing the problems, I kept wanting to try to do the parallel axis theorem with I and IG.
You can use the parallel axis theorem if that point of rotation has no acceleration.
If that point of
Some of the moments equals I, O, alpha only works if point O has no acceleration. That's when you use the parallel axis.
But in this, all points have acceleration. Right?
There is a whatever, yeah. Basically, yeah, there's no point that has no acceleration at this. There probably is, but it's a lot more work to figure out where that is.
Yeah. But like, if you did find it, for example, you could use parallel axis theorem about that point.
You could, but you have no external force. You have the external acceleration.
Okay.
You manage to eliminate the only thing you know from your equation.
Okay.
Okay, so it is a little tricky because there's no obvious force. Now, how would you check to see if you have compare F? What would you do? Yeah, so you need to check if mu s times n has to be greater than what? Not 0.
Mu s of k. Mu k.
Sum of the forces equals mass times acceleration. So it's equal to mass times a strut minus. So after you figure out what alpha is, you need to check was our assumption correct that we have static friction. As long as the maximum friction force is greater than mass times acceleration of center of gravity, then your answer is right. Otherwise, it's an easier problem. There is a rotation, but this becomes what? If we're slipping, that becomes, this is just mu k times n. And then you just take the sum of the moments about g. Right, if slipping, then this is the friction force, and so the sum of the moments about the CG equals I alpha equals mu k and I.
There'd be no acceleration.
There would still be an acceleration, but it's independent. Because if you're taking the sum of the moments about here, the mass times acceleration is times r, the distance between the center of gravity and the center of gravity.
Oh.
So you just have the I alpha term if you take the moments about here. Why did we take the moments about here initially?
So you can eliminate that.
So we can eliminate them, but now we know it, so it's a known, so that we don't want to eliminate it. And so then we take the sum of moments here and get rid of this unknown acceleration. So once you know you're slipping, the equations actually get a lot easier. It's just you need to assume that you're not slipping and then figure out where you need to right or wrong. You can't assume you're slipping and then go backwards. You have to assume you're not slipping and then figure out if that's a good assumption. But in mastering engineering, you just type in the answer you got when you're not slipping and say, oh, it's correct, and then, okay. That means they don't have to keep on going. So that's related to that. But it's a little confusing because it's not something we're used to. Because there's no external force. The external force is this mysterious friction.
Yeah. This is how we.
Yeah. Anyhow. So now we are dealing with a different concept, which is what? Impulse momentum. And we have linear momentum, which is mass times velocity. That's a vector equation. And we have angular momentum, which is
I omega.
Not alpha, I omega. Mass goes to I, velocity goes to omega. And so in this case, if we have an angular impulse, which is your moment times, not theta, that would be work, moment times time. The integral of moment times time is your angular impulse, just like the integral of force times time is your linear impulse. And so we're just playing the swapping terms game when we go to rotation to translation. So we have a moment coming from magic, a really small motor that has no ends. Anyways, we have a moment, we have a KO. What we want to figure out is the angular velocity after 6 seconds. So how would we know that this was an impulse momentum problem? You want a velocity, you're given time, and a moment. So when you're given velocities and times, you can either find the acceleration and integrate, or just use impulse momentum. So we're rolling without slipping. So A at this instant is the center of rotation. So what do we have? Now we have initial plus our impulse equals our final. The impulse momentum says initial plus the impulse 1 to 2 is equal to final. Initially, what do we have? Well, we're at rest, and so we start out with 0. Nothing initially. And then what do we apply? A moment. So we have our moment, which is 300 Newton meters, and we need to integrate that times dt. And so it'll be that moment times time. Anything else going on? Well, we're going to have a friction force. What direction is friction going to go? To the right. And what other things do we have? We have to integrate it. Then we have our normal, and we have our weight. And what do we end up with? Not acceleration, we end up with mass times velocity. We're moving to the right, and an I omega. That's still point A. Why do we like point A? There's 0 velocity there. And we can get rid of three unknowns. Right? So if we look at angular momentum, about A makes us really happy. Why do we like that? Because M, G, and N, and F all cancel. Right, we could just do the simple, angular momentum about the center of gravity is equal to I omega, But then we have this unknown force dt as well as this omega, and so we have simultaneous equations that we have to solve at the same time. So if we do angular momentum about A, we can get rid of 2 of our unknowns, and so life is good. What is our initial angular momentum about point A? So we have 0 plus what? mk so it's your moment times time, and so our moment is 300 Newton meters times our time, which is 6 seconds. The initial angular momentum plus our moment, and none of this will have any other angular momentum. That's equal to, what's our final angular momentum? It's I omega, that's true everywhere, plus mv times r. And they're both negative. And this is also negative. So life is good. So based on this, we get is equal to minus I. What's I? It's 300 kg times k 0.4 squared. So that's I omega. And we have mass times VR. What's V? V is equal to R omega. And so it's minus that. And so it's mass times R, which is plus 0.6 squared. So it's mass times k squared plus mass times R squared times omega. And this is a scalar equation. Why is it a scalar equation? It's in the z direction. So it's really a vector equation, but we're only looking at a special case. So basically, what we can get is that omega is, what is it? 300 times 6 over 300 times 0.4 squared plus 0.6 squared. This is meters, Newton meters, seconds. What is this, kg?
Oh, I see.
So that's meters squared. And that's equal to what? And so the power of the angular momentum as compared to the linear momentum is that we can pick our point wisely to eliminate some of our unknowns, and then it makes the other equations solving a little bit easier. All right. Similar, except what do we have here? We now have 2 gears. We're applying a gear, and this actually makes sense because we have a motor, which we're applying the gear moment from. And so we're given the mass and the radius of gyration of each of our gears. We're given the external moment. As we apply the moment, what's going to happen? A is going to start rotating this way, which means B is going to start rotating the opposite direction. And we want to figure out what's the velocity of gear B after 5 seconds if we start from rest. Time is a parameter, so that tells us we're using impulse momentum. Velocity of the gears using kinematics. How do we relate the velocity of the gears? The point of contact, so omega A times 0.1 is equal to 0.2 omega B, assuming that we're rotating in opposite direction. And then we can apply impulse momentum to both gears. If this was after a certain amount of rotations, then we can apply work energy. And if we're applying work energy, we'd want to do it in terms of the whole system, right? Why can we do it in terms of the whole system? Well, we have unknown reaction forces here and unknown reaction forces here. But these reaction forces don't move. So therefore, they do no work. However, can we, if we take the moment, say about right here, to eliminate these reaction forces, we still have this unknown reaction force here. So we can't, for impulse momentum, we can't take it as a whole system because we have too many unknowns to take our magic moment. So we have to still break it up into two parts so that we can actually solve the problem. So we have gear A and gear B. So 0 plus 0 is equal to 0. And we're starting at rest, so we both start. The initial angular and linear momentum is all 0. What is our impulse going to be? Well, we're going to have a weight. We're going to have a reaction. So this is NYA. We also could have an NXA. Right, we can have normal forces on gear A in both the X and the Y direction. Anything else? The reaction of the other gear, which is going to be pointing up or down?
Up. Yeah, it's up. It is up.
It's going to be pointing up. What do we want to call this? This is the force. And then anything else going on? Why is it up?
There's no.
Well, what's going to happen? I forgot my gears in my office. As this is rotating, it's going to push this gear down. So the equal and opposite reaction is pushing this gear up. So it's pushing the other gear down, so it has to the reaction force has got to be up. Anything else? The moment, yeah, we don't have the moment, we're not rotating. And so we have our moment. That's our free body diagram, and what do we need to do to make it an impulse? Integrate with respect to time. Fortunately, we're all constant, so we basically need to add a bunch of t's. So we add time to each of these to make it impulses, and what does this end up being? We end up with I times omega A. What about an MVA? No, the center of the gear is stationary, so we don't have any linear momentum. All right, what's happening on gear B? What forces are acting on gear B?
Weight.
We have the weight, so we have MBG, and then we also have NYB and XB. And then we have the force going down. Anything else? I think that's basically good. And what's that equal to? We have I omega b. And we're going to go the other way just because we've done our velocity analysis and we actually know what direction it's going to go. Okay, so now what do we want to do?
Would there not be a moment on that one from the, or is that just from the force?
The force causing the moment.
The force is what's causing the moment. And if this gear was actually attached to something, then there would be another moment at B of which you're driving, like your compressor pump or whatever. But we're just assuming that we just want to accelerate our gear just for a second.
This is times time.
And then, yeah, we need to make all of these times time. This is our free body diagram, which we need to add time to actually make our initial momentum. This is your impulse 1, 2. To get our final momentum. All right. Now, what tool do we want to take out of our toolbox? The angular momentum. This is our tool of the day. We could use linear momentum and angular momentum, but the other thing is we're rotating. So angular momentum, where do we want to take the angular momentum about?
Center.
Center, why?
Because all the things are going to go.
All a lot of unknowns are going about the center. So we have, for A, angular momentum. About CG, we have 0 plus, it's actually minus moment times time, because this is clockwise, and then it's minus force times RA times time. It's the moment is the force times distance times time. About the CG. And it should be plus. Because that reaction force will drive us counterclockwise. This is equal to IA times omega A. And then for B, your angular momentum. About your CG, what do we have? 0 plus F times RB. This has to be RA. So F times RB times T. That's equal to IB omega B. And this, yeah, has to be a minus IA omega A. So now we have two equations and two unknowns.
Omega A and omega B.
Omega A and omega B are our two unknowns. Well, no, we have a bunch of unknowns. We have three unknowns.
One is greater to the other.
Right.
Right, we have F, omega A, and omega B, and we also have omega A equals omega B times what?
Your ratio?
It's a ratio, so omega A is that times RB over RA, which is equal to 2 omega B. V is equal to R. The velocity at the contact point is equal to R omega.
Oh, okay.
And so RA omega A equals RB omega B. We already have that and negative signs in our assumptions of directions. So from here, what can we get? Here we have F equals IB omega B over RB. F times T is RB. Right? And so then everything goes into our big equation here, and we have minus M times T plus FT is IB omega B over RB. That's F times T, and that's times RA. That's equal to, what is that equal to? Minus IA times 2 omega B. Hopefully it's kilograms. So just make it kilograms just to make our life a lot easier. All right, we'll just take the second license. All right, so what do we end up with? We have, let's see, get rid of our minus sign, so we have M times T is equal to what? RA over RB is what? It's a half.
Oh, yeah.
Right, because A is smaller. So we have a half times IB, which is MB times KB squared. And then here we have what? And that's times omega B. And then we have plus 2 times IA, which is MA KA squared. And this is all times omega B. So from here we can calculate that omega B equals M, which is 10 Newton meters, times our time, which is 5 seconds, over 1/2 times MB, which is 50 kg, times KB is 0.15 meters squared, plus 2 times MA is 10 kg, times KA, which is 0.08 meters squared. I think that's everything on the bottom. And if we do the calculations right, I think it's 72.4 radians per second. There, radians. So whenever you're dealing with 2 gears, it became more complicated because for work energy, we could neglect our reaction forces, so we could do it as a system. But in terms of impulse momentum, we can't do it as a system, and so then we had 2 equations, and then that just got harder. All right, let's see. Slender bar rotates about an A. What is is its angular momentum with respect to A? Oh, we haven't started. All right, BB. For a slender rod, it's 1/12 ml squared is ICG.
It's not rotating about the same.
Yeah, it's not rotating.
It's not rotating about this. That's for the center?
This is about the center. We're not rotating about the center, so we have to use parallel axis. Oh. Yeah, that's why I did. It's the third. So if you remember, the slender rod has I about the end of 1/3 ml squared. What do we have to add to this? Plus mass times the distance, L/2 squared. So we have 1/12 plus 1/4, and that's how we get 1/3. As in the principle of work and energy, if a force does no work, it does not need to be shown in the impulse momentum diagram. Is that true or false?
What do you mean it does no work?
Force does not.
There's no displacement on no force. It's not that the force is zero, it's that the force doesn't move. We neglect forces that do no work in impulse momentum.
Okay.
All right, 5, 4, 3, 2, 1. Put this here now. Wow.
That's distribution.
Depends on the case. Well, no. No clue might be the true answer. All right, what happened here? Why did we have to break this up into two parts?
Because it would cause a moment.
Because these reaction forces, which do no work, do cause moment times time. So impulse is force times time. They have an impulse, they just don't have any work because there's no force times distance. And so it is false. We can't neglect forces that do no work in impulse momentum because it's a different problem.
No, I was trying to figure out.
All right, I think we have time to get started with the next one. Tell you what, we got 8 minutes. Let's look at a stop saw.
What?
Principle of constant. So this is sort of a, how can you use engineering to help you? Have you seen this before?
Yeah.
Heard of it? There we go. So what do we have here. A hot dog. What are these, a hot dog? But your finger would really hurt it. So the point of this is you don't lose a finger.
Whoa! I want to see him do it there.
What just happened?
Oh, it goes down.
Conservation of angular momentum is what happened.
As soon as there's some sort of.
He uses momentum to pull down.
Let's see if we can.
Like I didn't know.
How it works.
Yeah, it completely ruins it. I remember watching like a 60 minutes of commercial on it.
I want to
So
see
it's just
him
so
do it with their finger.
captivating. That's my finger on it and stuff.
So it stops where it's like a cheap.
It's a safety issue. Is this broke?
No, it just.
So here's what's
screens out.
happening underneath. If you can't do the book. I guess I'll have to. So when it,
How does it know?
how does it know it?
Huh.
So let's rewind it. So basically, pause. So what did it say? An electrical signal is applied to the blade. Right? And since you are a
Oh, yeah.
conductor, if it touches skin, then you're messing with the electrical signal.
Huh.
So it's constantly monitoring the electrical signal. Whenever someone messes with the electrical signal, like a hot dog or your hand,
What about like a piece of metal?
The hot dog is just conducting it through you, or what? How's it?
it will conduct through you, yeah. So it's basically, I think it's a capacitance, so as soon as there's a place for the capacitance to go to, it will know, hey, something's touching me that shouldn't be touching me. So again, this is a wood table saw. Can you cut metal?
No, what did it
No.
say?
So it wouldn't work on metal. It had to be a non-conductive material. Okay, so it now senses that you're cutting something you shouldn't be cutting.
Use your finger.
Not reliable.
So here it actually is that a hot dog?
Looks like a finger.
Looks like a finger.
Huh. So it actually fires it.
Fires it.
Whoa, what was that piece?
That's the aluminum brake.
Oh, it wrecks the blade, doesn't it?
It does wreck the blade, but it's better to wreck the blade than your
Yeah.
hand. It happened to a friend of mine in high school. Zip, cut off a couple fingers.
Oh.
They stuck it in a plastic bag full of ice and they were able to sew it back on.
So do you have to replace the brake every time?
You have to, yeah,
Just replace the brake.
you have to replace the brake every time, so it's best not to do it.
You refund it. Does not.
Yeah,
Keep your hand out of the blade, that's a general rule, but it does.
It's like $80 for a free oil.
So what happens? This goes back, this is now.
It is like a better one. As long as it's not glitching.
So he uses the momentum to pull it.
It yanks down. So let's see if we can. The next lecture is on conservation of angular momentum.
So you have to replace it.
So you do have to replace the brake, but it's better than replacing your fingers. These are cheap. So basically what's happening, this is spinning merrily along, and then what happens? The brake comes in. So we have a large force right here, large impulse. So what do we have? We have conservation of angular momentum about this point, because all the reaction forces are at this point. So what's going to happen? It's rotating, now it's rotating about this point, so now it's going to rotate. The angular momentum is going to drive this to go downward. And that's why it instantly disappears, because that large impulsive force is going to cause us to go downward.
I still want to see
So they do not hot dog, because every once in a while things don't work as they should. So don't put the Lord to your test.
What's the probability?
statistics. You know what?
Oh, you don't want to deal with that.
Well, like-
It's a 0.01% not working.
Wait,
How many people?